Hey, I'm Amanda Olson, mathematics instructor here at Metropolitan Community College. I am looking at problem 10 from section 4.4 of the Calculus online course. Let's just go ahead and work with this. So some resources that I also have next to me to do this problem. I have a formula sheet for trig, and I also have, so I have the trig formula sheet, and then I also have a table of integrals, some of the basic integration of trig function. So I have both of those. The table of integrals, if you're in my online calc class, you'll get you won't get the table of integrals. This table, you won't be allowed to use that on the exam. But the trig formula sheet, you should, if everything's working accordingly, have that on the test. So just to kind of give you an idea um, of what to do. So for this one, we're asked to evaluate a definite integral, and then it says use a graphing utility to verify your result. So for me, I don't require you to have a graphing calculator. So that part of the problem I would just ignore. Unfortunately, if we change the wording on the problem, it kind of eliminates some of the resources. So just ignore that portion of the wording. We will look at a graphing utility to verify the result, but you don't have to do that. That's not something I would expect you to do on a test if you encountered that. Okay, so first of all, there's two ways you can evaluate definite integrals. One of them is that you can substitute the bounds in right away, or you can substitute the bounds in later on. So we have these two bounds, pi over 4, and an upper bound of pi over 2. Our variable is with respect to x, dx. And so I'm just going to go look at the table of trig function. So we have a 2 minus cotangent squared x. And so I'm going to see if we have an antiderivative for cotangent squared x on the table. If we do, great, we'll just use it directly. But what I'm seeing is I don't see any cotangent squared x. So there's some different options of things. One of the things is I can look at, do I have any equivalent functions? And so when I see that squared, I automatically think of the Pythagorean identities for trig. So I go and look at some of those Pythagorean identities. You can see them. So we have here that 1 plus cotangent squared x equals cosecant x. So cotangent squared x, and there's variations that you can do for this, is going to be equal to cosecant squared x if I subtract 1 from both sides. Cotangent squared x equals cosecant squared x minus 1, which resembles slightly what our problem is. And then we have the antiderivative for cosecant squared x here. Okay, so I'm going to go ahead and use both of those parts. Going back to our problem, we're going to go ahead and replace, and we'll keep our bounds the same because we haven't adjusted, we're just using equivalent functions. We haven't changed our variable or anything like that. So we have here 2 minus, and then for that cotangent squared x, we're going to replace that with cosecant squared x minus 1. Okay, just double checking cosecant squared x minus 1 for our cotangent. And then the other thing that we also want to keep in mind is that cosecant squared equals negative cotangent for its antiderivative. So let's go ahead though and simplify this a little bit here. And we can distribute this negative and combine like terms. So again, I'm not changing my bounds or anything because I haven't changed my variable and I haven't applied the antiderivative. So then we have 2 minus cosecant, 2 minus cosecant squared x plus 1 when we distribute the negative to the 1, and then dx. And then we can go ahead and combine 2 and 1 to get 3. So we have pi over 4 to pi over 2. We have 3 minus cosecant squared x. When we combine 2 plus 1, we have all that dx. Change my settings so my font looks nicer. Okay, so then we can go ahead. We said that the derivative or the antiderivative, excuse me, of cosecant squared x, if you remember, that's cotangent x, negative cotangent x. We just want to make sure we remember that. So here we have the antiderivative of 3 is 3x if we're integrating with respect to x. And then for cotangent, this is going to be minus the antiderivative of cosecant squared is going to be a negative cotangent squared x. And then we evaluate that with x from x equals pi over 4 to an upper bound of pi over 2. So then here, we're going to go ahead and rewrite this as 3x plus cotangent squared x, and then we'll evaluate that from x equals pi over 4 to pi over 2. So then we want to go ahead and substitute pi over 2 in for x for both of those, and then subtract this expression with pi over 4 entered in for x. So that's how we evaluate definite integrals. We take the upper bound, we input it for our variable, and then we subtract with the lower bound input for our variable. So then we're going to have 3 times pi over 2 plus cotangent, mouse isn't very good, cotangent pi over 2 minus 3 pi over 4 plus cotangent squared pi over 4. Okay, so then we have 3/2 pi cotangent of pi over 2. So if we think about where pi over 2 is on that unit circle, let's just go to the unit circle. We want pi over 2. So going back up, pi over 2, we have this here. Cotangent is cosine over sine. So this is 1 over 0. So cotangent of pi over 2 is, since it's cosine over sine, it's going to be 0 over 1. And then for pi over 4, we have cotangent squared is equal to cotangent of that. If it's going to be that square root of 2 over square root of 2 is going to be 1. Okay, so we have 3/2 pi over 4 there. Cotangent squared, we have this is going to be 0, so we have plus 0 minus 3/4 pi. And then we said that this was 1, so we distribute that negative here and then here. So we have this as a minus 1. Going to combine 3/2 and 3/4. So 3/2 minus 3/4 is going to be 3/4 pi. Think of pi like a variable. When you combine the like terms, it's like 1.5 minus 3/4, and that's going to be 3/4. And then we have that minus 1. If you look at the answer key, the answer that they give, just so you know, is my stylus, I apologize, it's not working. Ah. The answer that they give, which I can't seem to type on here, is going to be, they just factored out, they have 1/4, 3 pi minus 4. And the reason is because they factored out a 1/4. So if we were to factor out a 1/4 from that one, it would be 4/4 with a 1/4 factored out. I didn't put my answer like that, but if you distributed the 1/4, you'd get the same result. You'd have 3/4 pi minus 1. So just kind of looking at that. The last thing is to verify using a graphing utility. So I'm going to go ahead and pull up a graphing utility. I'm going to use Desmos, which is free software. And then, they just want us to verify the result using a calculator. And then we can kind of look at what the area of the region would be. So the area of the region we were working with was, let's go, y equals 2 minus cotangent squared x. And then we want to evaluate that specifically from where x is equal to pi over 4 to where x equals pi over 2. Okay, and then we kind of zoom in on our graph. There's ways that we can shade it, but if I just annotate on the graph directly, we're looking at this region kind of right here. It having that value that we found, it seems reasonable. The 3/4 pi is a decimal approximation. We get about 1.35, which seems like it could be a reasonable. If we approximate that, with this, yeah, that seems to be 0.5 times 2. Yeah, that seems like a reasonable amount. So I'm satisfied with that answer. But yeah. All right, thank you.